Hello, welcome to my talk on boundary element method for wave energy conversion, part 3, boundary integral equations. In this talk, the detailed derivation of the boundary integral equations will be presented for the potentials of diffracted wave and radiated waves in wave structure interactions. As I mentioned in my previous talk, such a derivation was not made or wrongly made from what I can find from the books and the published papers, which all assume that the surface integrals at the far field for the diffraction and the radiation potentials would be zero. However, I found this would contradict to the Green's theorem, that is, the control surface can be either at the far field or in the near field. The derivation presented here is directly from the Green's theorem and the de-singularisation approach. And more important, the derivation solves the contradictions on why we can choose the arbitrary control surface. In my previous talk, it has shown that the de-singularisation approach on the fluid boundary, which consists of the surfaces, see the figure here, the control surface SC, the body surface SB, the free surface SF, the seabed surface SZ. And from the Green's theorem, this boundary integral equation is correct for an arbitrary control surface SC, whether it is at the far field or in the near field close to the body surface. We can separate the surface integral into different parts. The integral on SC plus SB, the integral on SF, and the surface integral on SZ. Since the surface condition and the seabed conditions are all satisfied for both potential function phi and the Green function g, thus, the surface integral on the free surface and on the seabed would be zero. If you like, you can find the proof in my last talk on Green's theorem and the Green's function. Then the boundary integral equation would be simplified as this. The surface integrals on SB and SC only, due to the choice of the specific Green function. And we will use this equation to construct the boundary integral equation only on the body surface SB. Therefore, next we will examine the surface integral on SC first, which would be the most important issue on how we can construct the boundary integral equation for the problems of fluid structure interactions. We can term this boundary integral equation as the general boundary integral equation, as this boundary integral equation can be applicable for aerodynamic problems. The difficulty in this boundary integral equation is the surface integral on the control surface SC, which is essentially an arbitrary surface. In reality, we do not actually perform the surface integral directly, but use the mathematical derivation to obtain the value of the surface integral on SC. The most important issue here is that the surface SC can be very large, such as at the far field or in any other site. For instance, in the near field, the only requirement for SC is it is large enough for accommodating the body surface SB. In the conventional derivation, some details can be found in the online book. The reference here. It is generally assumed that the control surface SC is at the far field when R equaling to the square root of x squared plus y squared becomes infinite, such that the diffracted wave potential and the radiated wave potentials phi j would be 0. In fact, they are infinitesimal, not exactly 0 from the mathematical point of view. Thus, the surface integral on the very large surface SC would be 0 for the diffracted wave and the radiated wave given in this expression. As a result of the integral on the very large control surface SC, we could have the boundary integral equation for the diffracted wave phi 7 and the radiated wave potentials phi j at this. It should be noted that the potential functions on the left-hand side are the values on the body surface SB. However, I will show you these equations are not correct because these conclusions is somehow contradicting with the Green's theorem. This is why I put the big question marks on these two boundary integral equations. The questions are caused by the result of the surface integral on a very large surface SC, which is supposed to be 0 as most researchers taken. Here, the questions are explained as follows. At the far field, the diffracted and radiated wave potentials would be infinitesimal on the large control surface. This is given by the far field condition. But we also note that the surface area for the integral is proportional to the large radius r, which would be very large. Therefore, the surface integral on SC might not necessarily be 0, since the integral of a very small integrand on a very large surface could have a limit value. This is true in this case. You will see this later in this talk. In deriving the boundary integral equation given by this, assume the 0 surface integral on a very large control surface. So we have the integral equation as this, as a special case. However, if we use this simplified boundary integral equation, we can deduce the surface integral on SC would be 0 if we compare this and this, regardless how large of SC would be based on the Green's theorem. In fact, there is no mathematical proof to show this surface integral would be 0, since we can imagine an extreme case for which the control surface SC is chosen to be very close to the body surface SB. Then can we expect that this integral would be 0? Now the question is, if the surface integral on SC is not 0, then what it would be? The problem can be solved if we employ the Green's theorem and the de-singularisation method. To show how we can solve the problem, here we need to construct a fluid volume V0 which would be enclosed only by the control surface SC, the free surface SF, the seabed SZ, C in this plot. No body surface SB is included in this case, because our target is to find the result of the surface integral on SC. Here, SC can be chosen same as that in the case for the general boundary integral equation, which would be large enough for accommodating the body surface SB. Here we can only imagine the body surface SB. The construction of the fluid domain V0 would be very important, and I will show how we can obtain the result of the surface integral on SC, especially the value of the integral on the body surface SB, because our target is to establish the boundary integral equation on the body surface SB only. Based on the Green's theorem and the de-singularisation approach, we could have the expression for the potential on the boundary. Here, phi on the left-hand side is on the fluid boundary on SC or on SF or on SZ. And we can also have the expression for the potential in the fluid given by this. And it should be noted, these expressions are correct for all potentials for incoming wave, the diffracted and radiated wave. Here, we apply the following boundary conditions as we used before. The potential function phi would satisfy the free surface and the seabed conditions. The Green function g would satisfy the free surface and the seabed conditions. By applying all these boundary conditions, we can obtain the surface integral on SF and on SZ would be both 0, expressed as this. If you would like to see the proof, please see my talk on Green's theorem and the function. Therefore, the surface integrals on free surface and on seabed SZ would disappear. As such, the integral equations can be simplified as this integral on SC only. The potential phi on SC on the right-hand side, given by this, and the potential function phi on the right-hand side in the fluid domain V0, given by this. In details, for the potentials of interest in this talk, we can have the expressions for different potentials on the boundary, especially on the control surface SC, since the potentials of incoming wave phi 0, the diffracted wave phi 7, and the radiated waves phi j all satisfy the free surface and the seabed conditions. And we can see here there is no special requirement on how we choose the control surface SC, whether it can be very large, for instance at the far field, or in any other site in the near field. The only requirement here for our problem is that SC must be chosen large enough for accommodating the body surface SB, because our purpose is to convert the surface integral on SC to the value on the body surface SB. But here we can only imagine the body surface. We list all these relations here, and we will see some interesting features for these expressions in the next slide. For the practical purpose, we may be more interested in the following expressions. Here, the potentials in the fluid domain V0, which are given by these relations. The potentials on the right-hand side. Here, phi 0, phi 7, and phi j are the potentials in the fluid domain V0. Now we can examine the special case when the control surface is very large, and on it the far-field condition can be implemented. When the capital R is infinite, the control surface SC would be at far field, and we can see the potential of incoming wave phi 0 would be given as this. Here, phi 0 is on SC on the control surface. Hence, for the potential of the incoming wave would not be 0 at the far field condition. This is understandable because the incoming wave is coming from the far field. The potentials of the diffracted wave phi 7 and the radiated waves phi j are given in this respectively. By applying the far field condition, the potentials of the diffracted and radiated wave on the control surface SC would be all 0, meaning the potentials of the diffracted and radiated wave would vanish at the far field. This is in accordance with the mass conservation and energy conservation. As such, on the large control surface, the potential would be only for the undisturbed incoming wave phi 0, while the diffracted and radiated wave would have no effect in the far field. But this does not mean the surface integral on the large surface SC would be 0. Another point here is that the incoming wave potential can be obtained from the singularities distributed on the very large control surface SC, given by this equation. As we have already shown, based on the Green's theorem, the de-singularisation within the fluid domain V0 would lead the potential in the fluid domain given by these expressions. Here are the potentials on the right-hand side. Phi 0, phi 7, phi j are given everywhere in the fluid domain. And it should be noted here the control surface SC is arbitrary, can be either at the far field or in the near field. Now we can imagine the body surface SB, but it is non-existent in here, thus in a dashed line. Since the imaginary body surface SB is in the fluid domain V0, therefore we can obtain the values on SB from the surface integral on SC given as these expressions. These are very important relations, and we will use them to construct the final boundary integral equation for the target potentials, the potentials of the diffracted wave and of the radiated waves. The potential of incoming wave would be known if the wave amplitude and frequencies are given, as we have talked about before. These are the equations to acquire the potentials on SB from the surface integral on SC, so that we are now able to construct the boundary integral equations on SB only. It should be noted here, SC can be chosen arbitrarily, hence the consistencies of the expressions are guaranteed. Now we are able to examine the problems of wave structure interactions. The first problem is for the diffracted wave, conventionally called as the diffraction problem. Here, we need to establish the boundary integral equation for the diffraction potential phi 7. Since both the potential phi 7 and the Green function g satisfy the free surface and the seabed condition, thus the de-singularisation lead to the boundary integral equation for the diffracted problem as this. And if we apply the values of the potential on SB due to the surface integral on SC given here, then we have the boundary integral equation for the diffraction problem as this. For the diffraction problem, the body surface condition would be given as this. This means when the incoming wave reaches the stationary structure, it would diffract the wave so to satisfy the boundary condition. This body boundary condition means the normal velocity on the body surface for the combined potential of the incoming wave and the diffracted wave would be 0. So applying the boundary condition for the diffraction potential, we have the final boundary integral equation as this. It should be noted here the normal vector n is defined as pointing out of the fluid. Here, we can compare the boundary integral equations from the different sources. In the famous boundary element method for wave structure interaction, WAMIT, wave analysis, MIT, and the reference tool, both give the integral equation as this, but no derivation was given on how this integral equation is derived. But we noticed here the normal vector in WAMIT is defined as pointing into the fluid, which is just opposite as the conventional definition of the normal vector, which is defined as pointing out from the fluid. It is not clear why the normal vector is defined as such in WAMIT, but it seems making sense. If we apply the opposite normal vector, then this integral equation and this integral equation would be exactly same. Another reference is the recent publication in 2016. Here, the boundary integral equation is same as that derived in this talk. However, the author didn't find the derivation in the reference, so the author didn't know how this equation is derived. And for a reference, I also find some more different expressions for the boundary integral equations for the potential flow problem in aerodynamics. This includes the famous Hess and Smith method, which is generally regarded as the first proposition for the Penner method for the potential flow, while the latter, pan-air, is a famous method for the potential flows with air compressibility. Again, the author failed to find how these boundary integral equations were derived. In solving the diffraction problem numerically, the Penner method can be used, for which the body surface SB is discretized into n small panels as seen in this plot. And on the small panels, we can assume the potentials phi 7 and phi 0, and their normal differentiations would be constant. Thus, the surface integral would be only for the Green's function and its normal differentiation. The discretized boundary element equation is given as this. Here, the index k indicates the Penner number of the source, and the index L indicates the Penner number of the target field. And we notice both summation here and here would be on L equals 1 to n, but not equals to k. So if we define the coefficient ALK equals to 0 when L equals to k, and ALK is given as this formula for L not equal to k, and BLK given by this formula, we can have the simultaneous equation for the diffraction problem, which can be used to solve the diffraction potential phi 7. From this simultaneous equation, it can be seen the normal differentiation of the incoming wave potential is the forcing function for the diffraction potential. If the wave is 0, then the diffract potential would be 0. The second problem is for the radiated wave, conventionally called as the radiation problem. Here, we need to solve the boundary integral equation to find the potential phi j. Since both the potentials phi j and the Green function g satisfy the free surface and the seabed condition, thus the de-singularisation of the Green's theorem would lead to the general boundary integral equation as this. The surface integrals on SB and on SC. And we also have obtained the values of the potentials on SB due to the surface integrals on SC. With this, we are able to construct the final boundary integral equation for the radiation problem. For the radiation problem, the body surface condition would be given as this. This body condition means that in the calm water, the structure motion is at a unit velocity. So the structure would radiate wave away to satisfy this boundary condition. Applying this body condition for the radiation problem, we have the final boundary integral equation as this. Note here, the normal vector is defined as pointing out of the fluid. By comparing to the relevant integral equation in vomit, again we can see the signs for the integrals are just the opposite for those boundary integral equations. Compare this and this. But we can take them as the same equation because of the different definitions of the normal vector on the body surface. But the author has no idea how this boundary integral equation is derived. Similar to the numerical scheme for the diffraction problem, we can use the same panels as seen in the figure to establish the simultaneous equation for the radiation potential. First, we can assume the radiation potential phi j and nj would be constant on the small panels. As such, the discretized boundary integral equation for the radiation potential is given as this. In here, we notice the summations are for L equals 1 to n, but not equal to k. And if we define the coefficient ALK as these formulas and BLK as these formulas, then we can build the simultaneous equation for the radiation problem given as this. This simultaneous equation can be used for solving the radiation potential phi j. From the simultaneous equation, it can be seen that the unit amplitude velocity of the structure is the forcing term. Therefore, if the forcing is 0, that is, when the structure is stationary, the radiation potential would be 0.